And now I'll show you how we can use the Y delta or delta Y transformation to solve a circuit. So we're given this particular circuit in here that has circuits that are neither connected in series or in parallel, like this one here, this one. Like you can look at it. None are connected in series or in parallel, and we're asked to compute what the power supplied by the source in here. And just a quick note in here, the source could have been easily drawn this way, plus minus. This is just a convention to say that this is a DC source that provides 40 volt DC, and this typically the circle can be used for any type of source. It can also be for AC sources. But anyway, so this is simply just a 40 volts, so this is higher than that by 40 volts, and we're asked to compute how much power is it providing to this particular circuit. And the simplest thing to do is to figure out an equivalent. I mean, this is a resistive circuit, so the easiest thing to do is just to figure out what the equivalent resistor is seen by the source, and we can compute the power it's providing to the circuit. So of course, there's multiple ways to approach these using the Y delta. What we have to do is we'll have to identify a bunch of Y and delta patterns in here. So we can see, if, for example, I have this particular delta pattern in here for these three resistors at 25, 40, and 37.5. I have another one in here, for example, that's a delta. And I can recognize a few of the Y's as well. So for example, I'm going to highlight them here. So this here is a Y. It doesn't look like a Y, but it is a Y. If you redraw it a little bit, it looks like a T. There's another Y in here. For example, you can just do this here. This is another Y. Okay, and probably I will be able to see another Y in here. So this is another Y as well. So there's a bunch of them in this circuit. Not everything and not all of them will be very helpful in our purpose. So you're going to have to do a little bit of analysis and just think a little bit about it before you actually go ahead and solve it. What I will do in this particular circuit is I will just focus on this particular red one in here. So I believe this will give me, if I converted this delta into a Y, so let me just draw that. If I convert this delta into a Y, and I'm going to draw it in red, I'll get like something like this. So this is the Y that I will get on these exact same ports. So I'll get the red instead of the 25, 37, and 40. And if you think about it, that makes the 10 and this particular circuit will be in series. The 25 will disappear, of course. So let me just make sure you'll see it. So the 25 will go away, the 37.5 will go away, and the 40 will go away. So those two will be in series, and I believe the 25 and this resistor will be in series, and then those two will be the ones that will become in parallel, as you can see in here. And then we can combine them in series with this one here, and then in series with that, and we'll be able to basically to simplify this circuit. All right, so let me just take this approach. I recommend that you basically try to take some other approaches, basically pick up some other deltas and some other Y's and see if they work. So what I will do is I'll basically call this one here is RA. This will be my RB, this will be my RC, and I'll try to compute what the RA and RB and RC. So again, this is here, I'm converting a delta to a Y. So I'm going to basically say the RA is simply, I believe it will be, since I'm interested in that, I'll take this resistor and this resistor, multiply them by each other, and then divide it by the sum. So that will become 25 times 40 divided by 25 plus 40 plus 37.5, and that will be the value of this RA. And that will be approximately 9.756. It's a little bit of, there's a little bit of approximation in here, ohms. Okay, we can do the same type of analysis for R of B. So R of B is here. Okay, so that means I have to multiply the 25 times the 37 this time. So what we do is we say 25 times 37.5 divided by the same sum, 25 plus 40 plus 37.5. And that will be equal to approximately 9.146 ohms. All right, we continue. RC becomes pretty much, it's here. So I have to multiply the 37 times the 40. So 37.5 times the 40, I keep saying 37 and 37.5, divided by the same sum, 25 plus 40 plus 37.5, okay? And that will give me 14.634 ohms. Okay, so I was able now to convert these. So what I'm going to do is I'm going to just redraw the circuit, and we'll do the simplification from there. So here's the circuit redrawn. So what I've done, let me just zoom out a little bit. So the 40 volts stays the same, the 5 ohms stays the same, and then the 100 and the 125, these ones stay the same. And then what we did is we converted this delta into this red y. This is the red y in here, so I substituted these values. So from now, it's just simple circuit simplification. So we can simply just say that these two and these two are in series, and we can then reduce those two, become in parallel, and then in series with the RC and the 5, and we'll be able to compute the value of the equivalent resistor. So let me just do that from there. So what we have is the R equivalent is simply, we're going to combine, I believe it's the 125, well, let me just combine it one step at a time. So we will have, I believe, let's call it R, let's call, did we call them R1, R2? We didn't call them, so we can use that. So R1 is simply 125 plus 9.146 ohms, and then R2 becomes 100 plus 9.756, and then these here, R1 in parallel with R2, will give me some sort of a value. Let me just compute that. Okay, so we got these values. Of course, I can redraw the circuit, or I can just basically, well, let me just redraw it for you. It's just simpler, so that you can see it. We'll do that. So here's a circuit redrawn. Of course, you should be able to see that these two are in parallel, and then the result will be in series with the RC and the 5 ohms. So we can do all of these in one shot. For example, we can just say R1 and R2 in parallel. Well, let me compute this. R1 in parallel with R2 is simply it will be 134.146 times 109.756 divided by the sum of these. 146 plus 109 plus 756, and that is equal to about 60.366 ohms or so. All right, so now the final one, and basically all the resistors combined. So what I have done is I just computed now the value of R1 in parallel with R2. All I have to do is just add 5 to it and that number in here. Okay, so that will give me the R equivalent is simply 5 plus 60.366 plus 14.634, and that will be equal to 80 ohms. So now we know that this particular source is actually seeing 80 ohms, and that's the R equivalent. So if this is 40 volts and it's seeing 80 ohms, we can figure out what the current is. So that's I of S. Well, simply I of S based on Ohm's law tells me that it is, I believe it's 40 times 80. Okay. Or actually, we're going to have to do V divided by R. Okay, so it's 40, so it's half an amp. Okay, and half an amp. Not 40 times 80, it's 40 divided by 80 because I is V divided by R. Okay, all right, so now we know that the current going through the circuit is half a volt, so we can, or half an amp, we can figure out the power of the source, which is simply negative for passive sign convention. Remember, it's like this is the current, it's going to the negative, so negative IS, which is 0.5 times V, which is 40, and what we get is negative 20 watts. That's how much power is being provided to the circuit.